this next example, we will see how, by determining formal charges, we can decide which resonance form contributes the most to the overall resonance hybrid. In this particular example, I'm looking at two resonance forms of a structure that involves oxygen, nitrogen, and chlorine. I've used this table to calculate the overall formal charges. This calculation involves, first of all, deciding what are the number of valence electrons in the neutral atom. We've done this before, so you can see, for example, that we have 6 for oxygen, 5 for nitrogen, 7 for chlorine, and that's true for both resonance forms. The next thing, however, is to determine the number of valence electrons actually owned by an atom. Now, there is a calculation that can be done for this, but I find it easier to come up with the number just by inspection. So starting, for instance, to determine that we have 6 valence electrons owned by the oxygen on the left-hand side here, the idea is that any lone pair electrons, of course, are owned by the oxygen. So this particular oxygen owns 4 electrons that are lone pairs. And then that oxygen will own half of the bonding pairs. Now there are 4 bonding pairs, so half of those 4 would be 2. So 4 plus 2 would give us the 6 valence electrons owned by that atom. In a similar way, if we look at the nitrogen, nitrogen owns 1 lone pair, so that's 2 electrons. It owns half of 6 valence electrons, so that's 3. 2 plus 3 gives us 5. The chlorine owns 6 electrons that are lone pairs, plus half of a bonding pair, so that's a total of 7 electrons. And then the idea is that we subtract from the electrons in the neutral atom the number of electrons that are owned by the atom. So in a sense, we're subtracting these numbers here. And you can see that there are no formal charges on the atoms in the left-hand resonance form. However, on the right-hand resonance form, if we look first of all at the oxygen, we can see that the oxygen has 3 lone pairs, so that's a total of 6 electrons that it owns, plus half of the bonding pair. So that oxygen actually owns 7 electrons. So 6 minus 7 gives us a -1 formal charge. The nitrogen owns 5 valence electrons, so it still does not have a formal charge. And then finally, the chlorine owns 4 electrons as lone pairs, and then half of the 4 bonding pairs, therefore a total of 6 electrons. 7 minus 6 gives us +1. So based on this, we can now decide which particular resonance form would contribute the most. As you might have guessed, any time that you have excess formal charges or formal charges over a neutral structure, that particular resonance form would contribute less. It would be considered to be less stable. Although it doesn't exist in its own right, it would contribute less to the overall resonance hybrid. There are some rules that are written down in your chem activity that guides you in this thinking. So number 1, when we draw Lewis structures or resonance forms of Lewis structures, we must include any non-zero formal charges. So recognize that we're going to need to go back to our representation of carbon dioxide because we are missing some formal charges. Next, a better Lewis structure will have complete octets. Now again, we don't completely understand, at least based on Lewis model, why an octet is particularly stabilizing, but we acknowledge that structures that have complete octets tend to be more stable. In this case, all of these resonance forms have complete octets. A better Lewis structure will have fewer non-zero formal charges. Therefore, the resonance form on the left-hand side is a better Lewis structure in that it has no formal charges. Now, if there are going to be negative formal charges, it would be better that they're on a more electronegative atom. You may recall that oxygen is more electronegative than chlorine. So in terms of where those formal charges are, it's better that the negative charge is on the oxygen versus the chlorine. In a similar way, it's better that a positive formal charge would be on a lower electronegative atom. An example would be if a positive charge was on a carbon versus being on, for instance, a fluorine or a chlorine. And then finally, Any non-zero formal charges greater than 1 essentially are not going to be found in a Lewis structure. So do not draw resonance forms that have charges of -2 and greater. So these sorts of rules can guide us in predicting which particular resonance form would contribute the most. And I think you would agree that this one, of course, would contribute the most. And therefore, we would expect that there'd be more double bond character between the oxygen and the nitrogen, and more single bond character between the nitrogen and the chlorine. Now let's go back to our carbon dioxide then. We acknowledge that these are resonance forms. We already know that the left-hand side structure contributes the most to the overall resonance hybrid. Let's see if we could predict that based on calculating the formal charges. So I'm going to use some short form notation here. So the N stands for the valence electrons in the neutral atom, and the O stands for the number of electrons that are owned by that atom in the molecule. And of course, we've got 6, 4, 6. This is the number of valence electrons that oxygen, carbon, and oxygen have in the neutral atom respectively. And of course, that would be true for both of the resonance forms. In terms of the number of electrons owned, well, the oxygen on the left-hand side and the left-hand side resonance form owns 6 valence electrons in that it owns 2 lone pairs, so that's a total of 4 electrons, and then half of the 4 bonding pairs, so that's a total of 6. Of course, carbon owns half of 8 bonding pairs, so that would be 4 valence electrons, and then the oxygen on the right-hand side of this left-hand side structure would also own 6 valence electrons. On the right-hand side, this oxygen owns 7 valence electrons, so it owns 3 lone pairs plus half of the bonding pair, that would be 7. The carbon owns 4, so that would be half of 8 bonding electrons. And then the oxygen on the right-hand side of this right-hand resonance form only owns 5 valence electrons, so it owns that lone pair and then half of the 6 bonding pair electrons, so that's 3 plus 2, so that equals 5. Now we complete the calculation. So the structure on the left-hand side has 0 formal charges, and of course the structure on the right-hand side does have formal charges, and we need to add that right next to the atoms that have those formal charges. And I would also encourage you to circle that so that it becomes very clear that those formal charges are there. So now that's a better representation of that particular resonance form. But of course, between the two resonance forms, this one would contribute the most.